So, we will come back, we are basically discussing several strategies based on protection and consequent deprotection of these several functional group based approaches. Now, in the protecting group chemistry, we said that you need to protect particularly chemical labile protecting groups or chemical labile functional groups with the help of some chemical reagents. Now, this protection gives you two extra additional steps, because you need to protect it or put a mask on it, and then subsequently you need to demask it. Though two steps are required, is very useful and advantageous in certain times, because many of the functional groups have similar kind of reactivity, and if you want to do a selective FGI on a particular protecting group without touching the other protecting group, you need to put a mask on that particular protecting group or particular functional groups. So, as we are basically discussing several problems, the next problem, which is again based on a protection group chemistry, the target molecule which was given to you is something like this. The structure of this target is a cyclopentane based pentene based compound, and you will find the structure is basically this. Now, if you analyze what you basically need, you basically need a addition of a methyl lithium on this carbonyl compound. Okay. The stereochemical aspects also will be basically considering. You see, both the OH are below of this cyclopentane ring, and the methyl which is coming is above the plane. Now, we said you basically need a intermediate of this. Now, how this intermediate can be constructed from this compound? There are two OH, 2 hydroxy, okay. And then one of this hydroxy needs to be selectively oxidized, means that out of this 2 OH you need to protect one of the OH selectively. So, basically what you need to do, you need to protect one of this OH as a OPG and keeps the other OH as free, and then you do a oxidation here, oxidation, and then you can basically correlate these things with this. Now, here a certain point needs to be considered. The particular starting material which we are discussing here having two different OH or two OH group, OH 1 and OH 2. Now, if you consider this molecule is basically having a nice C2 axis of symmetry, C2 axis of symmetry. Now, I am not sure how many of you have quite familiar with topicity or topicity parameters. Now, these two OH are basically in principle equivalent to each other. Now, the other consequences you might have if you have a compound like this, where both the hydroxy are above the plane. Now, these compounds having a sigma V. Now, sigma V means you can put a mirror in the center of the compound. So, left hand and right hand is basically having a mirror image symmetry. Now, mirror image are basically we called non-superimposable mirror images are enantiotopic to each other. So, that is why these two OH are basically enantiotopic to each other, and these two OH which are having C2 symmetry is homotopic to each other. Now, C2 symmetry means this compound you put a rotation 180 degree around this axis, you get a same compound. That is what these two OH are basically chemically equivalent, and they are termed as homotopic. So, I say OH 1 and OH 2 are homotopic. Now, homotopic means they are identical. We will be discussing this strategy little bit later on when you talk about stereochemical strategies. So, now what we say, you have this starting material OH and this OH. You react with one equivalent of TBS chloride with a imidazole. I say let us react initially. I say you might thought that which OH will be reacting. First say the right hand OH is been protected. In the other compound, the left hand compound, left hand OH will be protected. Now, in reality both these compounds are similar, is not it? You just rotate it, both these compounds are similar. That is the beauty of C2 symmetry, as both the parent OH are homotopic, no matter which OH are basically protected. So, both the compounds are similar. So, now try to do the same thing, you basically protect this OH as it is bulky TBS group. You use a oxidizing condition by pyridinium chlorochromate or PCC, you basically get a alpha beta unsaturated ketone. Now, the next synthetic reaction is using a one equivalent of methyl lithium. Now, this is the alpha beta unsaturated carbonyl, it is basically flat sp2 carbonyl. Now, methyl lithium can come from top phase or from the bottom phase of the cyclopentane ring. It is basically a cyclopentane is here, it can come from this top phase or the bottom phase. Now, see TBS basically blocked the bottom phase. So, bottom phase basically blocked by this bulky TBS group. So, methyl lithium has to come from the upper phase of this molecule, as the bottom phase is blocked by this bulky TBS group. And finally, you see the product which was given to you as a target, where methyl was above the plane. There is no way methyl can come below the plane. That is why the target molecule was given in this way. I said this is a nice demonstration of protecting group based chemistry, PGE based chemistry, and it also gives you an idea that how stereochemistry is very important in designing a synthetic pathway when you are talking about enantiomerically pure molecules. And particularly this case is very important, as the starting material is having a C2 symmetry. We will be discussing this part little bit later on when we talk about stereochemical strategies. Now, as we are discussing the protecting group based chemistry and how protection and deprotection helps in effective design of a synthetic pathway, next target which will be now given to you is basically a target molecule where you will find okay. This is the target molecule is given to you. Now, remember this is basically the protection group which we already discussed, is called acetonide, means that acetone is reacting with this diol to give this cyclic ketal. Now, PMB, what is PMB? PMB is basically a protecting group which is abbreviated as para-methoxybenzyl, is also a alcohol protecting group. The structure is CH2, this is called para-methoxybenzyl group. Now, the starting material which was, this is the target molecule, the starting material which was given to you for your synthetic exercises, we have basically discussed this transformation kind of thing earlier. Probably just by seeing the structure of the left hand side, you can easily find it out how the structures have been correlated with this target molecule by simple FGI. Now, what is this? This part is your Van Raff amide. So, basically this ketone introduction we will be using a Van Rapp ketone synthesis. Okay. That is why the starting material was given. And then you see this one of the secondary alcohol group has already having a TBS protection group, but then this alcohol is free, but as I said in the Van Rapp ketone synthesis you need to have a Grignard or lithium. So, which is a basic condition, probably you need to protect the free hydroxy group which might hinder in this Van Rapp ketone synthesis. So, what you do? You need to basically protect this diol as is acetonite. Usually in reality what was done? You treat, this is a TBS, TBS means silyl containing protecting group. The best way to treat this or remove these things, first you need to remove it, so that it become a free OH, then you protect it with acetonite. The best way the silyl can be removed is TBAP. It is called tetrabutyl ammonium fluoride, NBU4 N plus F minus. The fluoride ion having a tremendous affinity towards silicon. The silicon fluorine bond is very strong. The silicon fluorine bond is very strong. That is the driving force. So, normally if you have a fluoride which can clip oxygen silicon bond. So, first you treat with TBAP, and once you treat with TBAP you will find that the compound which will be immediately deprotected, the silicon ether will be deprotected and will give you the free alcohol. The remaining portion of the molecule will be won't affect it. So, you are basically getting a free 1,3-diol. Now, you react with acetone. Even if you do not have a acetone, you can react with another protecting group which is now I am talking to you is called this reagent, which is abbreviated as 2,2-DMP, 2,2-dimethoxypropane, which is basically a ketal or dimethyl ketal of acetone. Now, what is happening? If you take this compound in presence of H plus, this compound releases acetone with the loss of methanol. This is a trans-ketalization reaction. So, this methanol goes off, gives you acetone. Now, this acetone reacts with this 1,3-diol. So, remaining part of this molecule all similar, and basically you will now getting this 1,3-acetonite. This is OPMB and you are having these things. And next you basically react with this corresponding alkynyl Grignard or lithium in the Van Rapp ketone synthesis. Now, probably is the time that to explore the why Van Rapp ketone synthesis is so selective. I say the Van Rapp amide is basically a amide. Now, you react with any alkali lithium species or any Grignard species. So, initially what happened? You basically will be having this alkali lithium will come here and you basically get this O, this R prime is coming here, your N and methyl will be here. Okay. Now, see you are using a lithium or any metal. So, what happens? This particular metal lithium will make say cyclic chelate with this OMe and this O minus. Now, this cyclic chelate is very stable. So, you cannot further react with another equivalent of lithium or Grignard species, no matter how much excess you used. If you use 10 equivalent excess also, it will not react. That is the beauty of using a Van Rapp amide. Now, you can basically quench the whole reaction mixture at low temperature through acidic workup, Now, basically what happened? It comes here, gives you back, and basically you get the corresponding ketone back without getting the tertiary alcohol. Normally, if you react with ester and acids, you will basically end up with this. First you get the ketone, then it reacts with the another equivalent of Grignard or lithium to get to the tertiary alcohol. But Vendrabamide, as I said, once you get the cyclic chelate, the cyclic chelate was rock stable. No matter how much excess Grignard or lithium you react, it always stop this reaction here, then you just hydrolyze this intermediate to get back the corresponding ketone. So, this is the Venn Raab ketone synthesis which have been used very efficiently. Now, coming to our similar problem, we will now discussing another problem which was, let us talk about it, the structure is also a protecting group based strategy. Protecting group based strategy. The compound which was given to you is a target molecule having this structure. Now, if you closely analyze the structure, you will find that this structure basically is a cyclic acetal, the cyclic acetal. So, what you do? You just now do a retro 3 CH2 1 2 3 1 2 3, and then you see you put a OH here and then you put another 3 CH2 because you need 1 2 3. So, I say that if you disconnect the molecule in this way, it is basically a symmetrical diketone. You have a 3 CH2 left hand side, you have 3 CH2 right hand side. So, 3 CH2 COMe, 3 CH2 COCMe, and in between you have a secondary hydroxy group. So, one of these hydroxy will react either this way or this way, it gives you a cyclic hemiacetal. Now, this compound is basically a hemiacetal. So, now I said this is a symmetrical ketone. So, now if I need to disconnect this particular compound, we will be using a reagent something like this. We will put a 1 2 3 because you need a secondary alcohol here. And then you see that if somehow you are having a some species which is a diacceptor of a carbonyl, and then you have another exactly the same species of this. So, this reacts here, this reacts here, you basically get these things. So, now what kind of chemical compound or reagent will give you a double acceptor of this A1 type? It is basically again exploration of a synthetic equivalence, but in addition you need to also find it out there are some protecting groups. In reality, the synthetic groups of the synthetic exercises was done with this way. This starting material was easily available, and then as I said, this starting material you are trying to have some reaction on this side. So, you first protect this ketone group with a ethylene glycol. So, basically you protect the ketone. So, this is the protection of ketone and you get CH2 Br, CH2 Br. I think you need 1 carbon extra, is not it? Yeah, you basically need you have a CH2. So, you basically need a 2, yes, fine. So, then now you react with a magnesium. So, what basically you will get? You basically get this CH2 MgBr. Now, this is what? This is basically the, as we talked about earlier, this is a CH3 CO, CH2 minus, is a MgBr species or lithium species. And now you are reacting these species with a ethyl formate. Ethyl formate, how it reacts? The first equivalent of Grignard will come here, goes basically back and it goes up, and eventually you basically initial Grignard, what it comes, it will give you CH2, 3 CH2 remains, CH2 and basically get a this aldehyde. Then another equivalent of Grignard again attacks here, and then basically you get this OH, and then you get this CH2O this. Now see, this intermediate which you are talking about is almost arrived. Only thing is you need to demask this ketal group. So just treat with, do a forward arrow HCl. So basically get CH3CO, CH2, put a OH here and then C double bond O CH3. Now any one of this ketone will be reacting with this OH to give you a target molecule which is a cyclic hemiacetal. Now the target molecule structure, if you can again rewrite, it basically gives you this, this OH and Me. So 1 2 3 CH2, 1 2 3 CH2. So this OH reacts with either this or this, you get the target molecule. So this particular example we have focused about some of the nice chemistry which not only explains the use of protecting group, as well as we talked about a ethyl formate which basically serves as a HC double bond O OET, which serve as a 2 acceptor species 2A1. We earlier talked about a 2D1 species which is this one 2D1. Now this can act as a 2A1. This is also nice demonstration of synthetic equivalence. An ethyl formate you can basically react with a nucleophilic species by this way, by this it goes, it will basically give you RCHO. Now another equivalent of Grignard or any nucleophile species come here, and basically you can finally get of this corresponding alcohol. So this is a very nice way of talking about synthetic equivalence coupled with functional group based approaches. And in addition you have a protecting group chemistry where a ketone particularly was protected as its cyclic acetal with ethylene glycol. So, we basically use this chemistry to protect the ketone as its ethylene glycol to make a cyclic ketal. Now combination of all these strategies make the overall pathway very efficient and very nice to look actually. So, I mean if you combine the entire pathway, your pathway should be very much elegantly designed, and you will find the chemistry which you write in the 2-dimensional piece of paper should be visible to you, and then it gives a feeling that okay, this chemistry looks absolutely fantastic, you have to carry on the entire steps. Now, a similar kind of problem which I now picked it up, you will find this one is on the similar line, but the target molecule was something like this. The starting material I have also given to you, this is also falls under protection group based chemistry, PG based chemistry. We talked about protection group based chemistry, how different protection groups helps. The starting material which I have given you here is again is this. So, in reality if you see closely analyze this two compound, you will find that the target molecule is basically 1, 2, 3, 4, 5, 1 5 dicarbonyl compound, and the starting material which was given to you also a similar dicarbonyl compound, but only one double bond is there which needs to be removed from starting material to come to the target molecule. Now, as I said, this kind of transformation can be easily done if you do a simple palladium charcoal mediator hydrogenation. Now, I put a note that I said palladium charcoal and hydrogen probably is not available with you, not available to you too, is not available. Then will you stop this reaction in your lab, or you will try to find it out some other alternative? I will probably prefer the second alternative, whether some other reagents can be used to access this target. Now, I say the starting material is having alpha beta unsaturated ketone as well as a saturated ketone. So, their reactivity basically differs. So, what I first try to do, I will protect the saturated ketone with some reagents something like this. Now, this reagent is basically 1,3-dithiene which we earlier explored or explained. So, give you this. Now, I say you this ketone is still there, this ketone is still there. So, this alpha beta unsaturated ketone now you need to protect with corresponding 1,3-dithiene. So, it is basically a protection and deprotection, because you only need to touch the double bond without touching the both the carbonyl groups. Now, you have this double bond which is remains free and the both the ketone groups have been protected. Now, I say that palladium charcoal is not available to you. The best way you can do this reaction if you are having a nickel chloride and sodium borohydride in your lab. Now, nickel chloride and sodium borohydride combination basically gives you a nickel boride and hydrogen gas. Now, nickel boride is a nice black nanoparticle, is a blackish material, and hydrogen will be evolved in this reaction from sodium borohydride, and this reaction is very nicely can be carried out. If you do not have hydrogen gas in the lab also, you can do this hydrogenation by mixing with nickel chloride and sodium borohydride, which gives you nickel boride and hydrogen gas, and then it attacks this double bond to hydrogenate, and then you find that remaining other part, this is basically there are 2 CH2. So, if some CH2s I miss, probably I am little bit sorry, but that does not make any differences altogether. So, your thiol part remains similar. So, next what you want to make, you remove this cyclic ketal as well as cyclic 1,3-dithiene. You first treat with mercury, mercury will remove this one, and then you remove this ketal, cyclic ketal by acid treatment to get this target molecule which was shown here. So, you probably in this synthetic pathway we have seen that if certain reagents which is not available to you, you have to find the alternative pathway, and probably this is very environmental friendly pathway, because palladium charcoal hydrogen is sometimes can causes fire, because palladium charcoal is very difficult to handle in the lab. If your glass apparatus, your setup contains little bit of moisture, palladium charcoal causes instantly fire, and it basically is a explosive things. I mean, you instantly it catches fire, and the hydrogen is very flammable. So, need to be little bit cautious But the point is, if you do not have palladium charcoal hydrogen, we have alternative. You can use nickel chloride sodium borohydride system, which gives you hydrogen. There are other ways also. You can reduce this compound through diimide reduction. This is also a source of hydrogen, diimide. Now, diimide, basically this compound is diimide, which under the reaction condition gives you nitrogen as a gas, and as the hydrogen was there, this hydrogen is causing the hydrogenation reaction. Now, diimide you have to be, it is not again commercially available, you can easily make it in the lab. You take the hydrogen hydrate and you can treat with some particular reagents, you can generate the diimide. Those are the basically alternative reagents if you do not have palladium charcoal and hydrogen. So, we will try to continue our discussion on this functional group and protecting group based strategies. In the next week, we will talk about chemoselective protection and deprotection, and how you can functionally manipulate two different similar chemically reactive functional groups by suitably protection and FGI, then deprotection. So, till then, goodbye, have a good time.